about this biomolecule, because what we are going to talk here is just the tip of a needle. Okay, it's just tip of a needle, and beneath that needle there is an iceberg. So this is a huge area, but I will my task is to just introduce you guys about some of the terminologies, and I'm sure some of the terminologies you already know. Okay, so this is one thing. Another thing is to put the perspective of what chemistry or chemical knowledge that we have so far acquired or understood or learned, how this thing can be related to keep it or put it in the biomolecules or you can say biotechnology or in this field. So in biotechnology, you will see many more of these type of biomolecules, and many more reactions, because in our body and all those things, biomolecules, it is all regarding to our body, human body or animal bodies. All right, regarding to what is going on in our body. And most of this is related to food and of course medicine and all those things. So, but the food is the main thing that we will be more concerned about. What is happening when we are when we take food in different foods, and yeah, quite many things are going on in our body actually. So if we divide these biomolecules, it can be divided into three different segments or three different categories. That is fat and oils. All right, so there is two terms, fats and oils. We all know what is oils, and we also know what is fat, but probably we do not distinguish that. We do not distinguish in every day. We synonymously we call it fat and oils, but there is a distinction between them. And then proteins. There are different type of proteins. Protein mainly we get it from the animals, but there are some proteins that we can get it from our plants as well. And carbohydrate. And if we do the pyramid, and based on our diet structure or diet choices, mostly all over the world, we have in food pyramid, this carbohydrate is the most taken or consumed diet, that is carbohydrate. And then the proteins and fats and oils, the last one. And in between that, there will be vegetables, that is mostly is vitamins. And the other things, that is, we'll see it, that the other things, the highest amount in the vegetables that we find, does not absorb by our body. Okay, so what is the learning objectives? That what do you want to learn from here, these biomolecules? That we want to distinguish, we want to know what is lipids, carbohydrates, and proteins. What does it call? I mean, why, how they are different, right? And then the functional groups. What is again, the functional groups is here. That why do we not know the functional group? Because if we know the functional group, we will be able to predict or narrow down their reactions. That what type of reaction they will do, we can predict what type of reaction will occur for them. And the condensation reaction for the most of the for these fats and oils, for proteins, for carbohydrate, everywhere this condensation reaction is going on. And if you remember what is the condensation reaction, that we know that one molecule of water is being released from these two different type of reactant, and they become more condensed or infused together. That is the condensation reaction. And since there is a condensation reaction, there's a hydrolysis is possible to there. So if there is hydrolysis occurs, how does the hydrolysis occurs in these three different categories of the chemicals? That is the lipids, fats and oils, which is lipid. Lipid means fats and oils is under lipid, then carbohydrates and proteins. So what is biomolecules? This carbohydrate, protein, and usually we find it in our living animals or living beings, and it is very much related to if it's not consumed, it produces in our living beings. There are many other things that produces in our, but we can categorize them broadly into these three categories. Okay, so the essential role for this is the supplying energy, and all of them, they are supplying energy to some extent to our body, and then thus it is producing growth and repair of our organs, movement of muscles, because movement of muscles need energy, in the nervous system and our hormonal system, and the elimination of waste. All right, so all those things are done with the help of these three biomolecules, these three categories of biomolecules. So now if we want to go in detail into each of these categories, not details means just want to know what is inside each of the categories. So lipid, the fats and oils are actually inside, and fat is a solid. When we call it fat, it is solid, and when it's oils, it is liquid. It is liquid. So this is, both of them thing is under lipid. Now, if we want to ask you that what is the example of fat you have in your mind now, what can you come up with? The margarine, right? Or this type of butter. So these are the fats that is not liquid at normal temperature. And then for oils are oils, all the vegetable oils, all the oils that is liquid are liquid. And when you have oil, we are mentioning here, it is not the petroleum oil, right? Petroleum oil is hydrocarbon as well, but there are short chains, like we already have studied there. Butane, pentane, hexane, all those things, benzene. So all those things are petroleum. And for our body, we also need oil, just like the vehicles, but this oil is a bit different. Now, lipid itself can be divided into two categories or two parts, that are hydrolyzable and non-hydrolyzable. Hydrolyzable means they can be hydrolyzed, or they can be in the water, right? They can be in presence of water. They can be broken. In plain terms, we can put they can be broken in presence of water. So what's this? Those are that produces from the non-soluble part of some oils, the waxes, and triglycerol. Triglycerol is there is 3 hydroxyl group in this triglycerol, and we will learn more about it in when you go down. In a bit, actually, after a few slides. And phospholipid. There is phospholipids means there is a fat. There is one side of there is a long chain. First of all, that would be a long chain. This, you already know, right? This means there is a CH2 in each corner, right? You know this one, CH2 in each corner. So phospholipids are long chain. In one side, it is a phosphorus group, PO4. Okay. This type of groups in one side, another side is just a hydrocarbon. So this is a phospholipid, and then so that means it has a phosphate in it. So this type of hydrolyzable lipids, and non-hydrolyzable lipids is steroids, okay, and fat-soluble vitamins. For example, vitamin D is one of the fat soluble. Vitamin K is another for fat soluble vitamin. So these are the vitamins that non-hydrolyzable, and but they are lipid. So lipid means vitamin D, vitamin D, vitamin K. Those are also in, I mean, broadly in this fats and lipids category. And there is eicosanoid, and we will not be talking much about it. Okay, so fats and oils, we have already called it, and examples are, already we know that palm oil is also a fats, and cholesterol. We'll see a little bit more about cholesterol later on. I'll talk. So when fats, they are formed in a condensation reaction between glycerol and fatty acids. Now, there are two terms, glycerol, that I said that I'll talk a bit more about it. Glycerol, OL, right? At the end, there is OL, so that means it has a hydroxyl group. It must have hydroxyl group. But for this case, there is 3 hydroxyl group in glycerol. So you see this is 1 hydroxyl, 2 hydroxyl, and 3 hydroxyl group. So there are 3 hydroxyl group in this carbon-hydrogen backbone. So this another name is methane, ethane, propane 1,2,3 triol. So this is a glycerol. It's a commercial name, and this is a commercial name, glycerol, but this is more towards our chemical lab name, analytical name, that is propane 1,2,3 triol. So when this glycerol is reacting with, stearic acid, each of them, there are 3, right? There is no connection between this oxygen and carbon. So this is 3 different molecule, separate molecule actually. This 3 is separate molecule. So this one glycerol is added to these 3 separate stearic acid. Stearic acid is a fatty acid, right? Stearic acid is a fatty acid, and it should have from carbon 12 to 20 carbon chain length of carbon in the chain. So 20 times until, from 12 to 20 times carbon will be there. So C in this way, it will be 12 until 20. In between them, from 12 to 20, carbon should be in the chain. Then we call it, and at the end there should be COOH group. And COOH group, you know, this is a carboxylic group, right? This is a carboxy group. So this is a carboxylic acid. In another way, it is a carboxylic acid. So one side is just CH3, and then CH2, 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 CH2 until 20 carbon or 18 carbon or 15 carbon, and then at the another end there is COOH group like this. So when there is a hydroxyl group, alcoholic group, and carboxylic group together, we have seen it last lecture that there will be a condensation reaction, and then ester linkage will be formed between them because one water will be removed from here. So ester linkage will be formed. So this is how the tristearine is being formed. And since 3 of them, 1, 2, 3 stearic acid is attaching to these 3 hydroxyl group, 3 water molecule is being removed from this part. All right, so this is a tristearine because stearic acid is a stearine, and it could be trilaurine, trioleic, and so on. It depends on what type of fatty acid is being added or being joined, condensed together with the glycerol molecule. So this is how the fat is formed, and this is the vegetable oil. This is one molecule of vegetable oil that we use for frying or cooking. Looks like that, but this is not only the type in vegetable oil. You can find different type of this molecule, like a tristearine. You can find tripometic. You can find triolic, triolene, linolene. So all these things in oil, you will find this one. So now, can I ask you one question to keep you, awake? That why do you think oil is more viscous than water, although both of them are liquid? Can anybody answer me? Vegetable oil, like the cooking oil we use in our cooking, when we pour it on the frying pan, we see it is not quite watery like water. It's much viscous. Why? Anybody wants to give me a wrong answer? Only wrong answer will be accepted. Correct answer we will not accept. Anyone?
Is it because like they have longer chains like this and water is like only H2O?
Yeah, great. Thank you. So water is only H2O, that is small molecule first. Second, it has a molecular weight of 18, right? Only 18 molecular weight. But for this case, you see how big it is. Considering the water, one molecule to one molecule is almost few hundred times bigger. Comparing the weight. And another thing is, this chain is 17 carbon, right? So if I write 17 carbon, it will take a long time. So I just do this. You know that in each corner there is a carbon, right? So 17 carbon like this, and at the end there is glycerol, and this glycerol also has this carbon also has 17 carbon, and then this carbon also has 17 carbon, let's say 17. So what this long chain is doing is it is becoming intricated to the next, to the neighbor. So another from, let's say it is another glycerol, CCC, and from here it is coming inside here, like they are becoming infused to each other, right? And that is why they become more viscous. That is why they become more viscous. Oh, okay. So saturated fat, we know when we go to the market, how many of you buy that cooking oil? How many of you buy that omega-3, omega-5, omega-6 oil? How many of you buy? Or have you ever bought omega-3, omega-6 oil? No? So what does it mean? Omega-3, omega-6, it's not W, it is omega, yeah? Omega-6. So it is, the thing is, I'll come it later on, but before that, we go to the saturated answer. We already know what is saturated. This carbon-carbon single bond, that is unsaturated. And then here, in this 17 carbon long chain, there is no carbon-carbon double bond. All 17 carbon, 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 there is no double bond between them, right? There is no double bond. But if we see that there is a single double bond between them, that will be monounsaturated. Okay, and then polyunsaturated. So when there is more than one double bond, that is a polyunsaturated. Now, if we see that omega 3, that is the double bond from the, double bond in the fatty acid at the 3 position from the end of the chain. The chain starts, of course, with the where there is a carboxylic group, the carbon from there, and at 3 position from the end of the chain, there will be a double bond. For omega 6, it is a 6 position, there will be a double bond in the chain. So when there is omega 3 and 6, that means there is 2 double bond at 3 position and 6 position. And because of the double bonds, so you can anyway, so the thing is, when there is a omega 3 omega 6 or there is unsaturation, the oil is much more lighter. Viscosity is much more higher for that oil. That means it is, how do you say that, it's more watery, or it's running. The double bond, because of the double bond, the chain bends, right? The chain bends and they do not have the chance to integrate each other. Okay, later I probably will learn more later on. So examples of fatty acid. What are the fatty acids that we can find in our what do you call it, oil? So saturated fatty acid, palmitic acid, which is, this name is very much similar to palm, right? So in palm oil, there's quite much of saturated palmitic acid. Monounsaturated, which is oleic acid, and in soybean and other nuts and other plant oil, vegetable oils, which is lighter in color, this is this type of monounsaturated is considered more amount. But the lighter color, actually most of it that we see on our market, on the shop, the shelf in the shop, that is, or that is coming out from the factory, the oil that is coming out from the factory, much of it is bleached already. So it is not the original color, it has been bleached many times, or at least few times before it is being given to the shops. So that's why it's since more lighter color. Okay, but and polyunsaturated means there is one is linoleic acid. So oleic is unsaturated, one mono, and linoleic is both two polyunsaturated. That means two unsaturation are there. One thing for saturated fat is it is quite stable, since there is double bond. Again, remember the last class that we were talking, that when there is a double bond, they are more susceptible or more prone to make bonding. This double bond will break, and this carbon and carbon will make another bonding with something, maybe chlorine, right? Maybe chlorine, who knows? Or maybe one hydrogen, one chlorine, or hydroxide and sodium. So it will make bonding much easier than this one, because this is saturated, only carbon and hydrogen bonding, and carbon and hydrogen bonding is very strong, considered quite strong. So it does not break, or it does not do any reaction that we have seen already. So what happens is, those oil that has this saturated type of fat, they are quite stable, and that is why the palm oil that we use, it has a longer shelf life. That means if you even keep it for considerably long time, it will not go rancid, or it will not be what do you call it, what to say, it will not turn bad. It still can be used. For monounsaturated and especially for polyunsaturated fat, they are quite sensitive to light as well, and that is why you will see that olive oil always comes in in a black color of bottle, right? So that the light cannot go in. But sometimes for marketing strategy, or you can say it is to get the attraction of the potential customer, some of the oils, they are in a nice transparent bottle, and the water, I mean the oil looks very clear, is next to water, is so transparent. Although there is aesthetically is very plausible, but problem is the light is passing through, so maybe it is not that stable. And another thing is, since they are saturated, this palmitic acid that is in palm oil, they will be stable at high temperature. So for high temperature, for frying, like deep frying, all those things, this palm oil is better in terms of quality. Of course, monounsaturated, polyunsaturated are better. They have some good thing for our health, of course, but problem is they go rancid or they turn bad very easily at low temperature. Even I mean, consider low temperature, and the more polyunsaturated will become saturated. Right. So if you are using polyunsaturated and you are using high heat, then probably it is not a good idea. So that's why olive oil is usually used in the salad dressing, or yeah. Right, so common fatty acids, is it? Already you have seen it. Common fatty acids, that is the vegetable oil, and it says that circle an ester functional group. So we know that this is an ester functional group, but it will be wrong to do in that way. We should do in this way. This is as ester bonding. This carbon has two oxygen, and this oxygen is bonded to another carbon, right? If I just take this much, it does not give me any good idea of what it could be. It could be hydrogen here, right? And it could be anything, sulfur, not sulfur, sulfur does not. But it could be anything, so that it is not a ester bonding. So it is better to show that it is having a good bonding with carbon and carbon. In between there is oxygen. Okay, so this is it. This fat saturated or unsaturated? Will there be any carbon-carbon double bond in between them? Because we see that how many carbons are there? There are 14 plus 1, 15 carbon. And then oxygen, hydrogen is 14 times 2, 28 plus 3, 31. So does it fulfill CnH twice n plus 1? So 31 plus 1, that's 31. Why it is not 2? Usually the saturated hydrocarbon, the formula is H twice n plus 2, because here is another one we are not considering here. Here, this is another, it is attached to carbon, and this carbon is attached to oxygen. So we are not considering that carbon and that bonding. We are cutting it off here. So this carbon, oxygen, carbon and oxygen is not considered, and that is why is CnH2n plus 1. So the formula gets a bit changed than usual for this case. If it breaks down, that fact it breaks down, what will happen? All right, actually that fat gets broken down in our stomach, intestine, with the help of some enzymes. And if it is broken down, where will it break down? Of course, it will break down from here, where it's connected at the first place, right? So it will produce an acid, carboxylic acid, and it will produce an alcohol, OH here. So the same thing. So it will go back to a triglyceride, triglycerol, which is propane 1,2,3 triol, and the rest part it will produce carboxylic acid, each of them. And another product that will be formed, not product formed, but the reactant that is required is water, because the OH and H is coming from water, and this is called hydrolysis. Hydrolysis means the water becomes dissociated, water becomes broken, two parts, and those two parts are attached to those two reactant. So that is called the hydrolysis reaction. So cholesterol, now we have understood what is the glycerol or palmitic acid or fatty acids. So cholesterol, I'll talk about it, that it is one of the most feared compound that we call it, right? The cholesterol is high, cholesterol is high. Well, not all cholesterol is high. Actually, LDL is high better than HDL, isn't it? Or I'm making a mistake. Either one is good and either one is bad. So there is two types of cholesterol, HDL and LDL. But all the time, actually, our body makes cholesterol, produces each cholesterol every day. All right, and that cholesterol is necessary for our what do you call it? Digestion system first, our sex hormones, and then also for our antibody, natural antibody for our body, natural antibody to protect us from all those type of bacteria and viruses. So this is important, vitamin D. So, and you will see that it is very much similar, the cholesterol and vitamin D is very much similar to each other, almost everything. Here there is one bond is open, one, and here there is one more CH3CH2 came in to join it here. But interesting thing is, it is almost very much similar to that of the sex hormone that we have for male and female, for testosterone and estrogen. For ladies, for female, it is very, very much similar, right? Its hydroxyl is replaced, this whole group here, and for male is hydroxyl is used by keto group. So that is the difference. So you understand that it is very much similar, the structure, the base structure is very much similar actually. So we know that cholesterol is, actually we need cholesterol, but the problem is excess in everything is bad. You know, everything, if it's too much, it is not good. So if say that is very high cholesterol is not good, it's not always good to, I mean, consider in that way, because cholesterol is also important for us. And another thing is, we just need to make sure that we are having enough, not too much, and our body can produce this cholesterol, transform this cholesterol to those vitamins or hormones or for that function in our body. To get vitamin D, to produce vitamin D, we need to go to the sun, because our body cannot produce without the sunlight. So we have to go to the sun to produce the vitamin D, and thus it will produce the sex hormones. And yeah, so this is the, I mean, but if too much, it start to stack up in our core, I mean, in our blood vessel, coronary thing, coronary blood vessel. Not only the cholesterol, actually, it is the shock that our the blood vessel gets. Shock, different type of shock, different ways for stress, tension, all those things, and it gets cracked, so calcium start to build up there, and that is how our blood vessel gets thicker, and thus the blood flow is reduced, and that is why the heart we get the heart attack at the end. So it is not always the cholesterol is the bad thing, but cholesterol is mostly good, but if too much, it is bad thing. So we have to make sure that we eat and we do exercise We go to the sun, we get our enough sun every day, and yeah, that should be good. So how does this fat gets digested in our human body? We have seen that fat becomes smaller chunks, or hydrolysis happens, and then it gets in presence of water and some acid, it gets to fatty acids, broken down to fatty acids, and then glycerol. Glycerol is it doesn't do anything. It is quite what do you call it, inert thing. It just go out from body, but the rest, it remains in our body, and it is that provide us that the energy for our body to react, for movement, for many things. It gives us energy. So in alkaline condition, the hydrolysis reaction occurs, and with the help of some enzymes for fat and lipid, actually lipase, the enzyme is lipase, which is responsible for breaking down this fat in our body. Lipase, the enzyme. So we will learn about enzyme. What is enzyme later on? So lipase enzyme helps us to break the fat in alkaline condition, and it is glycerol and fatty acids it becomes, and then the fatty acids, it is stored or it is absorbed in our body, and it produces the energy, or it delivers the energy that is needed to our adipose tissues in our body, or animal, in a living body. So that is how the fat is important. Fats and oils are important to produce energy in our body directly, that energy. And it does not, the good thing is it does not produce any sucrose or glucose, or it does not store for a long time in our body. For carbohydrate, natural polymer, carbohydrates are the natural polymer as cotton, cellulose, and all those things, that is carbohydrate. And as its name implies, that carbohydrate is made of carbon, hydrogen, and oxygen. So this carbohydrate does not mean that carbon and hydrogen only, there is oxygen as well. All right, and the formula is CxH2OO, water, but sum of Y, and the XY are the whole numbers. Like lipids, these carbohydrates can be different categories, right? So they can be monosaccharide, disaccharide, polysaccharide. Mono, di, and poly, we understand already that mono means one, di means two, poly means more than two. So monosaccharide is the simple sugar that we eat every day in the morning. We take with our tea or coffee. This is the monosaccharide. Disaccharide is also, we can find from the plants, and then we can have it. But this is when there are two simple sugars are attached together. But when I'm taking the sugar or saccharide, we will be amazed to see how many types of simple sugar are there. All right. Okay, so polysaccharides, when there are more than two are there. Examples of sugar are the glucose, and we all know the fruit juices that any type of fruits that we eat, sweet. All right, so this is glucose, and fructose, and galactose. All right, and galactose doesn't find, we cannot find it naturally in its pure form. We need to isolate it and produce it, formulate it, and produce it, not formulate. Okay, so And there is disaccharides are maltose and sucrose and then lactose. Maltose, the name has implies that malts, from malts we can get the maltose. For sucrose, it is from the sugar cane, sugar beet. This is sucrose. This is a disaccharide. That means two monosaccharides are together. And lactose, from milk, there is from in milk there is a lactic acid, right? So there is lactose as well. It's the carbohydrate in the milk that we can get it. And polysaccharides, there is starch, cellulose, glycogen, and all those things that we think. And this glycogen is the thing that energy stored in the animal, in the liver and in the muscle, which too much in turns to be fat tissues. Okay, so structure of monosaccharide. We have seen the chemical formula, right, before. The chemical formula for all of the monosaccharides are C6H12O6. But before this, before chemical formula, we have seen the simple formula. What does it call? Yeah, that CH like 5, right? And then it can be C2H10. What is it called? That type of formula, I forgot the name. I've forgotten. Anyway, but we discussed in the lecture 1, the first week of lecture. Okay. So the monosaccharide, from there we came to this chemical formula, because this type of formula, it was not good enough for us to tell us what was the thing that we are looking into it. Empirical formula. So this is from empirical formula we came to this chemical form. This is empirical formula, right? Empirical formula. This is chemical formula. This chemical formula, and then even from empirical formula was just a general one. I mean, just to give an idea of how many carbon, how many hydrogen, how many oxygen was there. So we we said that we shouldn't be using the chemical formula to understand what is this actually. Now we are here to the chemical formula. Isn't the chemical formula is, although same, it is not giving us an idea, or we don't understand why it is different from one another. So for this case, we have to go to this structural formula. And all this structural formula, we will be amazed to see that each of them, all of them has 6 carbon. 1, 2, 3, 4, 5, and 6. There are 6 carbon in each of this corner, right? And similar 12 hydrogen and 6 oxygen as well. But the behavior or reactions to glucose and even galactose is so similar, but still different, because in our body or in a living body, the reactions are not drastic. It's very soft, you can say soft reaction occurs in our body, and it matters. The structure of these compounds, it matters. So you see that fructose, it is obviously different shape. That is why it is different from them, because the 2CH2 is hanging on the either side of the oxygen, and it is a pentagon size. Although it's 6 carbon, right? It's 6 carbon, but still is different structure. For glucose and galactose, do you see the difference? at this position, the hydroxyl is here, is just become inverted. The hydroxyl goes up here and hydrogen comes down there. So it becomes the galactose from glucose. That's it, the difference. The rest, everything is same. And that makes the difference. Okay, so this is the monosaccharide. When two monosaccharide attach together, there will be disaccharide. When two monosaccharides, so glucose and glucose can be both two glucose or glucose plus fructose or galactose plus fructose. I mean, anyway, if different, I mean, all any of these monosaccharide attached to each other or infused to each other, it will be a disaccharide. It will be disaccharide. And again, this is a condensation reaction. So condensation reaction is water is going out from the reaction, right? So one thing is when the glucose, I mean monosaccharides, not only glucose, but for this case is glucose. When glucose is reacting, you see that only the reaction is occurring in hydroxyl and hydroxyl. Some students write here, they take this oxygen as a reaction, the space, I mean, the point the reaction is occurring. No, never. It will be not. It is not that easy to break this oxygen bond, but hydroxyl, because the water will be going out from here. Water will be going out from here and they become infused together. So now this bonding, this oxygen, because HOH, OH, H2O means 2H and 1O goes away from here, go away from here, only left with one oxygen. And this oxygen becomes sandwiched between two carbon. Here is the carbon, right? And there's a carbon as well. So this oxygen is holding two carbon from two sides, or it becomes sandwiched between two. So in this case, it is an ether bondage. It is an ether bondage or glycosidic link. So this is a glycosidic link. This is important for biochemistry or molecular biology. All right. So this is very important for us to remember. What is the? Yeah, this is ether and glycosidic bondage. Okay, so the same thing happens when glucose and fructose is occurring. This oxygen and oxygen, this bond will never be disturbed. They are still as it is, because if it is broken, the chain opens up. It is not a saccharide anymore. Yeah, so this is glucose and fructose, and the same bond is ether bondage. This is the ether bondage as well. It's the ether bondage as well. It's occurring. So now you know, I mean, for fat, for sucrose, we are having too much of condensation reaction, right? So if even we eat fat and we eat sugar or carbohydrate, we need water. For carbohydrate, the water is released. For fat, the water is being taken away. How? So that is why, I mean, if we take too much carbohydrate, we need to, so our body excrete too much of urine. The urine is produced from here. Okay, so polysaccharide. Now, we have seen mono, di, and now is polysaccharide. So do you see that one is starch, which is our food, all the food. I mean, the bread, cakes, rice, noodles, cookies, then what else? Biryani, everything. Everything that we eat are the starch. This is cellulose. This is not our food. We cannot digest this thing. Our human body cannot digest cellulose, but it is okay, and we live on starch. So can you see the difference? Can you tell me what is the difference between them? Can anybody point out the difference? Here. What is the difference between them?
The position of the CH2OH.
Yep, thank you, Eric. So you see, for here, all the CH2 on the one side, all right? It is on the same side for them, for starch. But for cellulose, it is on different side. Here, CH2. And again, it is here different. In a 3D model, it does not look that plain because it is on a 2D model. But if you see a 3D model, you will see in a different way. But the idea is it is all on the same side. So this is why our body cannot dissolve, digest this cellulose. And if even we eat cellulose, it should go out as it is. And for starch, we break it. Our body breaks it and produce it, the glucose, monosaccharide. And if we need that energy, because the glucose that is broken from here, it provides us energy for our body function to go smooth. But if we do not need, our body does not, I mean, if we're idle, we do not do anything, we just sit, do video games and on computer, or just watch videos, don't do anything, then what do? Our body does not need that much energy. What does it do? It store it. It keep in our body, store, and that thing, our muscle does not know what to do with this, so it keeps inside, it stake it inside in our muscle as a fat molecule. So that is how the fat molecules increases. So if anybody said like, okay, I don't work much, I don't do video, I want to do video game, I don't want to eat. That is not good idea as well, because if you do not eat in a balanced diet, not your body only, your brain also need energy, right? So you have to have balanced diet, and your brain works better because we have our potassium gate, sodium gate in our brain, our nerve system, many other things. So the gate opens and closes when we do some exercise. So I think we should always get some exercise, yeah? At least not very, I'm not telling you to go to the gym and do the weightlifting, but you know, you can do some simple, but still do some exercise. Okay, so example 2 says that difference between 3 types of carbohydrate, blah blah thing. You can get it done later on. Okay, now digestion of carbohydrate. So carbohydrate, starch or glycogen is digested using the enzyme and water. Of course, it will be broken to smaller chunks first, that is the maltose, to big chunks, and then it goes to the smaller chunks. So to produce glucose. And then glucose, actually, it gives much energy to our body. And that is why you will see that in the supermarket, there will be some glucose. Okay, in the supermarket, you can see some glucose. That actually gives a direct and fastest energy, because our body produces glucose to get the energy out of it. So if we provide the glucose, it gets the direct energy from here, right? So yeah. Now, example 3 says the structure of lactose is shown in the figure below. Lactose undergoes hydrolysis in the digestion process. Hydrolysis. So hydrolysis. What does hydrolysis means? Right. So hydrolysis means water will be broken, and then one hydrogen will come here, another hydroxyl will be attached here. This is how hydrolysis is broken. This is a glycosidic bonding or ether bonding. Anyway, so these are the things that you can do. Okay, so another interesting thing is lactose intolerance. Lactose is a carbohydrate, and it is a disaccharide as well. So these different types of disaccharide, and why will it cause to some different type of reaction to our body? When we are eating the same saccharide, it does not cause that type of reaction because of the orientation. That is why I'm saying the structure, to know the structure of the compound is also very important. Just because of the different structure and in the 3D dimensional, actually. That's why we have to have a good imagination, actually, how the 3D looks like, could look like, or should look like in that way too. So anyway, so lactose sugar is kind of sugar, and then when it breaks down, it produces saccharide as well. But some of us, we do not have the enzyme to break the milk, the lactose, and the enzyme name is lactase. Some of our intestine, of our body, our intestine does not produce enough intestine to break this lactose in the milk completely. So it is not a big problem. Some people, some people has this type of problem, but it is not a big deal. It is not a big problem, right? It is just a shortage. But since this lactase does not do any other thing, only that it breaks down the milk, so it is not a big problem. So just don't drink milk. And this lactose intolerance it means that stomachache, low motion, and all those things, that vomiting sometimes. So those are things that we cannot absorb or digest milk or milk product. Now we are moving towards protein, right? So every living things and all the muscles, every living organisms is made up of these proteins. Okay, and it's a polymer, big chain. It's quite big chain actually, and it's built up from a small monomer called amino acid. What is an amino acid? Since it is an acid, we understand there should be one hydrogen donating group that can give or donate hydrogen ion, right? So that should be an acid. So since it is an organic acid, it is a COOH. Organic acid in our body, human body, it cannot be in our stomach there is, but not in our muscle. This cannot be sulfuric acid, and nitric acid. It is a carboxylic acid in our stomach. In a body. So this amino acid is made of a carboxylic group and amino group. All right, this amino group, and of course there is a carbon chain. And there is a side chain. It can be, cannot be. Can be or cannot also. But the thing is, it can have a side group anyway. So can I take 5 minutes break? Yeah. Before I go to the break, can you go to mentimeter.com and try this example? code is here. All right, I submit the code to you. Please go to mentimeter.com and try. And I'm sharing the screen with you too. All right, so please try. Okay, I can see many of us has voted, 7 of us out of 8. 8 of them voted, but let's see what is the right answer. next slide. Okay. So here you can see is the answer. In this way, we can find out that the number of double bonds should be 3. So 1 and 2, those who have put the number 1 and 2, good, thank you for participation, but the answer was not quite correct. Okay. All right, so we go back to our lecture slide again. Okay, so proteins are the blocks that I mean the main ingredients that making the building blocks of our body, of our living bodies, and they are made from condensation reaction that occurs between amino acid, right? Small monomer molecule called the amino acid, and the polymer of the amino acid are the proteins. So when there are many amino acids together, joined together due to the condensation reactions, they will become a bigger protein. So simple amino acid is a glycine where there is a carboxy functional group, and then there is another amine functional group as well. Okay, so carboxy functional group and amine functional group both are there. So this is a simplest protein that we can have, which is glycine. And the chemical name, this is the commercial name, that is the glycine, but for chemical name that we understand that it will be 2-amino-ethanoic acid. So this is a hydroxy group, the carboxylic group at this position. So we start counting from this side, and then first 2, an amino group at 2 positions. So 2-amino, and the backbone is ethanoic acid. The second example of simple protein is the alanine. Alanine has a 3 carbon chain, and this again 1, 2, and 3. So it's 2-amino propanoic acid. All right, 2-amino propanoic acid. This is the alanine. This is simple proteins. So types of protein and their functions. What do they do actually? Structural protein, the protection, support, and movement. All the structures in our body, the skin, bone, cartilage, all those things. All right, feather, cocoons, insect, exoskeleton, all those things, muscles, all those are separate different type of proteins. And different type of protein means they are still amino acid and carboxylic group there, but their length, the amino acid length may be bigger, shorter, or their branching may be different. The structures are different structures. Structural proteins. So enzyme, we haven't talked about enzyme. We are going to talk after 2 slides or 1 slide probably. So enzymes are also protein, and they use as a catalyst, biological, but enzymes are a very big molecules itself. So they're catalyst actually. They do many reaction under this biological reaction under enzymes, under the influence of enzyme. If no enzyme, the reaction does not take place. because biological reaction, I mean, although catalyst, but why it does not take place? Because the biological reactions are actually very quick. It takes all very long time. So if no enzyme, it will take probably very long for the reaction to occur, which is equal to no reaction. Hormones, all the hormones that our body has, do our body function also based, of this protein. Insulin is one of them, right? Transport, movement of between the cells and our neurons, all those are made of this protein and all those things. So here the snake venom, you can see that it is a protein for the snake or for this scorpion, right? Snake, scorpion, all those things, they are the protein for themselves. They use this protein, their venoms or spider, for their bodily function. But when it is injected to other animal, it is, since our body, like human body, our body does not know that protein. It is, what do you call it? Our body becomes shocked because the sudden intrusion of this different type of protein. So that is why we get the venom effect in our body. But otherwise, it is working fine for them. Just like other biomolecule, protein also get condensed, and different type of proteins. It can be amino acid 1 or amino acid alanine or glycine, a different type of small proteins, amino acids. They will infused together and produce dipeptides, and the water molecule is going out. So like glycine and alanine, when they are coming together, this hydroxyl group from this carboxylic group, yeah, and this hydrogen group from this amino group, they will get infused and then produce a dipeptide. For this case, it is a peptide bonding. These bonding, students always make mistake of these bonds. So we have to understand, or we have to remember that this is a peptide bonding for protein. In protein, it is a peptide bonding. And this protein can get really very long, and it can have different type of proteins in it. So glycine, alanine, cysteine, serine, valine, all those type of different proteins can be condensed together and produce a very big different type of protein. And that is what I'm saying, that our neurons, our the crab shells, and our limbs, our muscles, tendons, different proteins they are made of. Hair. Okay, enzymes, biological catalyst. That enzymes are a very big protein molecule, but very long, very big molecule actually. And enzymes, it causes the reaction to go very fast. 10 power 20 times faster. Can you imagine this number? 20 times means after 10, you have to add 20 zeros. How big is that number? Trillion, 100 billion, trillion, something like that. So it is the reaction rate becomes very fast with this help of the enzymes. But the enzymes are, problem with these enzymes they are very sensitive, very specific, and very much operate under mild condition. All right, so they are proteins, of course, and when the condition is not mild anymore, when the condition becomes harsh, they will get denatured. Denatured means one example of denaturation of protein is that the eggs. If we boil the egg, the same egg, if you put it in the incubator, it will produce a chip. And if you put that same egg in a 100 degrees centigrade, 80, 90 degrees centigrade water, it will become boiled, egg boiled, right? So the egg gets boiled or become hard, the yolk and the white part, what is called cytoplasm, protoplasm, both of them becomes hardened just with the help, in presence of heat. So because of this heat, this protein becomes denatured, all right? And when it becomes denatured, it cannot do its normal activity of catalytic activity. And that is why when we are having fever, high fever, and the most of the protein, this enzyme, they work better 35 to 37, around that temperature, 35.5 to 37.5. It's very narrow range. It's around 2 degrees only. They work better in that range. If it gets higher, lower means gone, we are dying, dead. If it's higher than 38, that's when you have high temperature, high heat in our body, the enzymes get denatured. And many of our body function does not do. We will have constipation, we'll have start to vomit, we'll feel migraine or headache, many things will happen just because that the enzymes are not working perfectly. So this is it. And how enzymes work, they're a big molecule, so they surround the substrate, means a targeted molecule that the reaction will occur for this substrate, right? The reaction will occur on this substrate. So the enzyme will surround the substrate like the reactant, because it's a big molecule, they surround, and they will single out first that 1:1:1:1, like they will break it chunks, and then they surround each of the small chunks, small chunks. Then they will, and after that, they will, the smaller chunks are separated, isolated, so their reaction is happening there. And once the reaction occurs, these enzymes open up, they release it, go to bind the next one. And that is how the enzyme works actually. So it's very much selective. One enzyme like lipase will not go, lipase is for lipid, right? It will not go for a lactase thing. It will not go to any other to break protein. It is only for that type of oils and fats. So yeah, that is very much selective, very much area specific. Lipase enzyme in detergent. For detergent, this actually Danish company Novo Nordisk, they bring this idea because our clothes, when it's stained, it gets different type of dirt, right? It gets oils, and that is why it becomes dirt. Oils and hydrocarbons and all the suits and many of the things, dirts. So they started to infuse this catalyst, enzymes that can break down these oils and these dirts and then the sticky things. It breaks it down to small chunks, and that is how it can get, it's easy to get washed by this. So this is an interesting idea actually they started with. Okay, you know this answer actually. So example 5 says that A, B, C, D, E, F, G, H, I, J, K, L, whatever, which molecule of polysaccharide circle the glycosidic link on the diagram above. It's already here. This is a glycosidic link, and this is to me it looks like a starch, isn't it? It isn't starch. It would be cellulose if this CH2 was moved to here and hydrogen goes to there, it would be cellulose. So every unit, it is alternatives. Anyway, which of the two molecules are given to produce a saturated triglyceride when react. Name the type of reaction. Condensation. Oops. Protein is formed from carboxy and amine. So carboxy group and amino groups are there, and they can produce another type of protein when different type of protein molecules are attached together. So all these things I think is enough for today or for us. And do you have any question, anyone? Is there any question anybody has? If not, then I'll stop it here today, and then you know that we will have our tutorial on Thursday instead of Friday. So Thursday 9 to 11 p.m. Sorry, a.m. And the last tutorial. So I hope that you will be there. I will see you there. But once again, it is the last lecture for today. I mean, for this semester. But I'm not done. I will be here. I am here. If you need a session with me, or if you want to have some discussion with me, please email me so that I can arrange a time, and I will have a talk with you. No problem with anything. Right? So all the best. Take care and have a nice evening. And I will see you on Thursday morning. And once again,